So here again, we have our strong electrolytes. We also have obviously non-electrolytes. Non-electrolytes, not too much involved here in what we're going to talk about. But again, those are guys that basically will stay together. They still will dissolve in solution, but they will not create any ions. We also have weak electrolytes, and weak electrolytes, again, will mainly stay together. Where do those go? So something like hydrofluoric acid is a weak electrolyte. In solution, it will break apart a little, but pretty much you will mainly have this guy still together. So if you were to look at sort of a beaker of that, you would mainly find those HF units still floating around, but you would have some of those ions kind of floating around as well. So it is still a electrolyte because it's still able to produce a little bit of ions, but it's nowhere near as strong of an electrolyte as something like sodium chloride, which will mainly break apart. So most ionic compounds are strong electrolytes. They're going to break apart 100%. Most like weak acids and weak bases are typically a lot of your weak electrolytes. So when they're in solution, they are going to mainly stay together. Now, water in terms of solutions, and a reminder, I think we talked about at the end last time, a solution is typically the things that get that aqueous symbol next to it. And it is as a result of, for example, dissolving something in a solvent like water. And water is a really good solvent for polar and ionic compounds. And that is because, again, ionic compounds work really well with water because water itself, based on our geometry that we talked about and bonding, is a polar molecule where the hydrogen side is more positive and the oxygen side is more negative in this particular case. So what happens when you do go to dissolve some type of thing like sodium chloride is the sodium ion and the chloride ion will again get surrounded by the water molecules, and that's basically what helps it again dissolve. And as we've seen a couple of times and probably have talked about a couple of times, it's really not a chemical reaction happening here or a chemical change. It's more of a physical change. We just cannot see the sodium and chloride ions anymore because they're basically surrounded by a ton of water molecules. The negative ion would be surrounded by the positive side of water, which is the hydrogen ion, or the hydrogen part of water, and the positive ion would be surrounded by the negative oxygen in this case. It does two things. Again, it allows it to dissolve, and it looks like it just disappears. It really doesn't disappear. It's just surrounded by a ton of water molecules that you no longer can see it anymore. And we know that because we did a couple experiments at the beginning where you put it in your evaporating dish and you heated it up, and as you heated it up, you evaporated off the water molecules, and that allows those two ions to come back together, and you would see that solid sort of reform after you evaporated off the water. So again, that's more of a physical type of change. And that is, again, the hydration part here of those water molecules surrounding those ions. We help things dissolve usually, right, by stirring. And as we stir, what that's essentially doing is putting a ton of water molecules all over the solid. And we also are adding energy as we do that, so it allows it to dissolve a lot better. Now, as I mentioned before, acid and bases are also electrolytes, and we do come across a lot of acid and bases, especially since it's a whole classification of reactions, which are acid-base reactions. And we have strong acids and weak acids. We also have strong bases and weak bases. A reminder that there is sort of a list of 6 strong acids, which is really a good sort of list to remember. It will do good in this class and other classes that you take. That is hydrochloric acid, nitric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and perchloric acid. So this list of kind of 6 strong acids is really an important one to remember because you can make a pretty good guess that if it is not one of these 6, you're probably dealing with a weak acid. So just by process of elimination, knowing these six allows you to sort of determine, what you're dealing with in terms of the other. When we talk about bases, again, a lot of our strong bases do come from group 1 and 2 on the periodic table that have hydroxide, things like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. Again, basically, if you go there on the periodic table, lithium, sodium, potassium, hang right there at calcium, and come down, any of those guys with hydroxide are typically strong bases. And both of those sides there, the strong acids and the strong bases, are strong electrolytes, which in solution will definitely 100% break apart into ions. You're going to get none of those whole units basically still together. Acetic acid is a weak acid, and again, much like hydrofluoric acid, it will break apart a little bit into these ions, but this is again mainly what you're going to have in solution. And we typically see weak electrolytes, as we talked about, with these arrows that head in both directions. That's a reversible reaction. There's a forward direction and a reverse direction. And it's kind of like a two-way street. The reaction heads both ways, as opposed to a strong electrolyte where the reaction basically heads in one direction. So electrolytes do play a part in different types of reactions, and we're going to talk about how to classify reactions. And as we will see as we go through this chapter here, there are multiple ways that you could actually classify the same reaction, and it just kind of depends on what you're looking at. But when we talk about classification of reactions, there's really kind of two big categories of reactions. There are double displacement reactions and there are redox reactions. And when you boil down pretty much all reactions, basically all reactions basically occur for really three reasons is pretty much why a reaction might occur. One reason why a reaction occurs is the formation of a solid, which is sometimes referred to as a precipitate, the formation of water, and lastly, it is a transfer of electrons. And these are really three reasons why pretty much a reaction takes place. You could almost boil it down to any reaction, one of those three things are sort of happening. And when we talk about that, the two sort of big categories of reactions, kind of big umbrellas for which more specific classifications fall, are double displacement reactions. And as we'll see in a double displacement reaction, which is pretty much the reaction you did in lab on Monday, you have two ionic compounds. And always when you have this situation of two ionic compounds, basically the partners switch places and you make two new ionic compounds going on here. And the result of this sort of switch that occurs in a double displacement reaction is, in some cases, you will get a solid that forms, kind of like what you did when you got the yellow lead 2 iodide form the other day. And that is kind of one of the reasons, again, why a reaction takes place. Also, when you do this reaction, it is possible that instead of a solid, perhaps you make water as one of your products. And that is, again, the second reason why a reaction takes place. So double displacement reactions basically account for two of the three reasons why a reaction takes place. Either you're going to result yourself in a solid, or you're going to make water. And those are two of the main reasons what happens. The third reason a reaction takes place is a redox reaction, as we'll talk about. And that is where we find transfer of electrons in this type of reaction. And redox reactions basically account for the third reason why a reaction takes place, which is a transfer of electrons. And between these three guys, obviously, these are two big umbrellas, and then we're going to have some more specific classifications that come along. So the first type of reaction we're going to specifically talk about is a precipitation reaction, and this does fall under the double displacement umbrella. So a precipitation reaction like the one you did the other day is a double displacement reaction. and that is AB plus CD. Once again, going to switch partners here. And we're going to get an AD and a CB. And in this particular case, the result of this reaction is going to be a solid being made. Yes, sir. No, it's just it is just really a switch of partners that happen in that, and the result of that is you get a solid or water being formed based on the switching of those partners. In redox reactions, as we'll talk about, you basically have one thing basically transferring electrons to somebody else. So like when sodium and chlorine come together, metal and nonmetal, metal going to transfer those electrons over to say chlorine, which is a nonmetal. That's a redox reaction that's going to happen. And because of that, what happens is the charges actually change. If you want to think about that, really the oxidation state changes. In a double displacement reaction, there's no real change in the charges on either side. So for example, the example that we did, or the experiment we did, was you took Ki, right? And you basically reacted it with lead to nitrate in this case. And again, this is a double displacement reaction. These two guys basically switch partners. And the basic unit of this ionic guy is a potassium ion and an iodide ion. The basic ions of this guy is a lead with a +2 charge and a nitrate with a -3 charge. So they just switch partners as they're swimming around kind of in the solution, and we get KNO3 here, and we get PbI2, which is our solid and our precipitate that's made. Now what I'm saying is over here on the left-hand side, that is the charges and those are the ions. Over here on the right-hand side, they're the same thing. Nothing's really changed. This is still +1, this is still -1 for the nitrate, this is still +2, and this is still -1. So there's no real change in charges or anything like that in a double displacement reaction. What does happen though is when, for example, as you saw, when the lead and the iodide ions are swimming around in the solution, in the beaker, they're like, cool, I want to kind of get together with you two and make this not red solid, but obviously a yellow solid that you had when you did the experiment. So because of certain properties, when these ions find themselves floating around with each other, they want to come together and either make a solid. It could also happen when you have something like H plus and OH minus in the solution floating around. They're going to definitely attract it to each other, and they're going to want to come together and make water. So, but nothing really changes in terms of charges, and no electrons are really being transferred in this type of reaction. Yeah.
Just to clarify, so it doesn't necessarily have to be negatively charged ions that switch. It can be two positives and two negatives are together.
The two positive ions always switch partners. So remember, they're still ionic compounds, which means you can only put together the positive and negative. So something's going to happen here. Because these guys started together, they can't stay together. So the only option for the potassium is the nitrate, right? It's the only other negative guy that's floating around from different from where he started. And the only option for the lead is the iodide because, again, it's a different partner. So the way people remember it is basically the two positive ions basically switch partners. And that's always what happens in this reaction. Yeah. Other questions? Now, a precipitation reaction, as we just saw, forms a precipitate. And again, the abbreviation for a precipitate is a PPT. And again, that is a result of what we'll talk about, which are sometimes referred to as solubility rules. And there are certain combinations of ions when they do get together, will basically jump out of solution. They'll kind of bind together and come out as a solid. Now here is this reaction, which is very similar to the one we did in lab, except there was sodium iodide instead of potassium iodide in this particular case. And when we look at this, this is actually what is known as the molecular equation. And the molecular equation is basically all the formulas written like we normally would. This guy's also aqueous here. And when we look at the molecular equation, it doesn't really adequately describe what is truly going on in the beaker when you do this. So really, when you throw these guys into a beaker, you take your lead to nitrate and you take your sodium iodide in this case, and they both go for a swim here. Because they are strong electrolytes, because they're ionic compounds, they are again not going to stay together. They're going to 100% break apart into ions. And basically what you'll have at that point are the lead ions floating around. You'll have some iodide ions floating around. You'll have some sodium ions floating around. And you'll have some nitrate ions basically floating around in this solution as you kind of dump it all in there. So we could actually write an equation that basically describes what is actually going on in this reaction. And this one, like normal, is what is known as the molecular equation. We can actually break apart things that are strong electrolytes. So really in solution, this guy is lead with a +2 charge, ion floating around in that beaker. There is technically 2 nitrate ions floating around. This guy is also a strong electrolyte, which means it will break apart in solution, and that will give you 2 sodium ions floating around and 2 iodide ions floating around. Do the little aqueous symbol next to it. Now, when we get to this side, what's going to happen really in this beaker is once you kind of dump all that together, there is a really strong attraction between these two guys, and they are going to come together, as you saw, and make that yellow solid, and they will actually precipitate out in the solution as a solid. And because of that, we actually don't break it apart when we write this type of equation. So when you write this type of equation, anything that is a solid, because it's a solid, it's basically staying together. It will not break apart in solution as ions, really. And you would keep them together. Other things that you would keep together in this type of equation that we're writing right now is things that are weak electrolytes. So if you have anything that's sort of like a weak acid, weak base, a weak electrolyte, you would keep it together. Anything that is a pure liquid, like water, you would also keep together. And occasionally, most of the time, gases you would keep together as well. So anything that is sort of a solid or liquid, you definitely would keep together. This guy is a strong electrolyte, which means it would break apart into a couple of sodiums and 2 nitrates in this case. Now, when we look at this equation, this is what is sometimes referred to as the total ionic equation. And some people just call it the complete ionic equation. Some people just call it the ionic equation. And this equation basically describes sort of what happens when you dump all these things into a beaker together and what is floating around in the solution. And when you look on both sides of the arrow in this particular type of equation, you should be able to find ions that look exactly the same. So for example, here we have 2 nitrates, and we also have 2 sodiums. And those are exactly the same. And you'll also notice if you do this equation correctly, you'll have the same amount of those ions on each side. So I got 2 on each side, right, of each of those. These guys that are just hanging out, actually in my picture right here, they're essentially just floating around, right? They are basically watching what's going on. And they are what are referred to as spectator ions, right? If you're a spectator, you're just really watching what's going on. They are not directly involved in any type of product formation. So really what's happening in this reaction, right, is that solid being formed. The sodium ion, the nitrate ion has really no business making the solid. It's not doing anything to make that solid. So what we do with the spectator ions in this reaction is, because they're not really important in a sense, we do cross them out on both sides. And that actually leaves you the third type of reaction, which is a reaction or an equation that basically tells you exactly what is going on in this reaction when you mix those things together. So basically what is happening in this reaction is the lead ion from the lead nitrate, 2 nitrate, is going to find the iodide ion from the sodium iodide, and they're going to come together basically to make that solid or that precipitate, and that is what is known as the net ionic equation. So the net ionic equation is the equation that basically cuts out everything that's not important and basically gets to the heart of this is essentially what the reaction is basically those two ions coming together to make that solid. So molecular equation, you write everybody just like normal, use the proper formulas, you balance the equation. Total ionic equation, you break apart anything that is a strong electrolyte, anything that is a weak electrolyte, anything that's a solid, liquid, or gas. Essentially, you keep those together. You would not break them apart. And anything that's a liquid as well. And you find your spectator ions, cross them out, and what you're left with is ultimately the net ionic equation, which again describes pretty much this is what's happening in this reaction when you put these two things together. Any questions on that? Yeah.
How do we know, like, how do we know that lead and iodine are both together rather than like I know
It's a really good question. And the answer to that question is we're going to see in a few slides down the road here what are known as solubility rules. And solubility rules basically tell you that question when you're talking about ionic compounds. When you put these two ions together, would you expect a solid to form or not form? So there are certain rules that basically kind of give you an idea as to what would make the solid. For example, one of the solubility rules is anything in group 1, like sodium, they're soluble in everything, which means it will never make a solid. So by process of elimination, we know wherever sodium ends up is not going to be the solid. And iodide, for example, is soluble in everything except for 3 things: silver, mercury 1, and lead. So it's one of those things that when you put together with I, you make a solid and stuff like that. Yeah. Other questions? All right, so that is our total ionic equation as we just talked about there. Again, we can find our spectator ions, which in this case is our sodium and nitrate. And once again, with the spectator ions, as I mentioned, you really should have the exact same numbers of those ions on each side. And if you find at some point you don't have the same number of those ions on each side, then you really probably wrote a wrong equation or you didn't balance it correctly. So if you properly balance the molecular equation, you should end up with equal numbers of those ions on each side. All right, then we get to our net ionic equation here. All right. So to answer your question, she wasn't too bad, I think. Not too long I've run around. To figure out whether or not when we kind of combo these guys together, will we get a solid or not? We do have to use what is known as solubility rules. And solubility, again, is the definition of solubility is the maximum amount of solute that will dissolve at a given temperature. So solubility is based on temperature. And as we'll talk about maybe in a later chapter, the higher the temperature, usually the more soluble some type of solid is in a liquid. Kind of the lower the temperature, not as much. When we talk about solubility, there's sort of 3 classifications of solubility that we talk about. Things that are soluble means that you would not expect a solid. So things that are soluble, you would not expect a solid. These are the guys that get the aqueous symbol next to it. Basically, you're going to make a solution, no solid. There are things that are insoluble, and things that are insoluble means when those two guys come together, you expect a solid to form. So that's going to be your lead and your iodide, for example, as that last example. And those are the guys that will get a solid next to it. There is a third sort of classification that you probably won't come across all that much, but it is out there. And that was referred to sometimes as slightly soluble. And slightly soluble basically leans more towards it is insoluble. So most times when you see something that's sort of classified as slightly soluble, most people will kind of put that more in the insoluble category, like it's going to make a solid and stuff like that. Now, all things, as you'll learn eventually if you go to 1B, even things based on solubility rules that say when you put these two together, you'll get a solid always, is not really 100% true. There are a lot of other factors that play into whether or not you actually see the solid or not. But for this class, next class, pretty much you can follow the rules, and that's what you can sort of think about. When you get to 1B, you'll talk about things that do affect solubility, and even though technically things should make a solid, things like pH, things like concentrations play a big role as to whether or not you'll see it. So here are the solubility rules, which you do need to know. So let's talk about what this means. Compounds are soluble. So these guys will essentially mean you will get an aqueous solution, no solid, basically. So anybody in group 1 is going to be soluble. So if you see a formula with anybody from group 1 on the periodic table, you pretty much do not need to look any further. You already could just put the aqueous next to it. You know you're not going to get a solid. So as we were talking a second ago, when we saw that sodium with the nitrate on the right-hand side, as soon as I saw the sodium, I don't have to look any further. I know that's not going to be the solid in that case because of the solubility rules. Ammonium, so this is NH4 plus, also going to be soluble in everything. There's no exceptions in this case, so there's no exceptions, which means if you see anything with ammonium in it, you know it's going to be soluble as well. Those that contain nitrate, chlorate, and perchlorate are also going to be soluble in everything. So let's just say, for example, that sodium nitrate that we saw earlier, you weren't sure about the sodium, but as soon as you see the nitrate, you also know it's going to be soluble. That's also why I knew originally when we looked at on the reactant side, this guy, I saw nitrate, and I know that this guy is going to be soluble, and it is going to be basically an aqueous solution in this case. Most that contain chloride, bromine, and iodide are aqueous, but when you get to these three, there are exceptions, and the three exceptions are silver, that is mercury 1, and that is lead 2. So most of the bromides, chlorides, and iodides are going to be soluble. But if you have any of those guys with these guys, then they will become insoluble and actually be a. That's why on the right-hand side of our example we just saw, this is iodide, which is soluble in everybody except lead, which makes it an exception, and it's going to be insoluble and actually be a solid in this case, which is what the S stands for there. Most sulfates are going to be soluble. Some exceptions are calcium and silver sulfate, which are slightly soluble, and barium, mercury 2, and lead sulfate, which are insoluble. Again, slightly soluble in most cases are considered to be more insoluble than soluble. So these are some rules of guys that are normally soluble. If you come across anybody with an exception, it does the opposite. So instead of being soluble, it becomes insoluble when you look at this. Any question on those rules there? Now, there are some things that are typically insoluble when you have them. So let's take a look at some of those. Now, these are guys that are typically insoluble, which means you are going to get a solid that's going to form, and that is hydroxides. So hydroxides are typically insoluble except if they are hooked up with group 1. And again, group 1 is the rule from the previous slide, which is soluble in everything. So that is why when we look at something like sodium hydroxide, hydroxide is normally insoluble, but in this case it is hooked up with group 1, which makes it then soluble. Yeah. And again, it basically falls back to group 1. Now, do I have to remember this rule for sodium hydroxide? No, I just have to remember the first rule, which was sodium soluble in everything, right? So that's all I have to remember in that case, right? Now, we do have barium and calcium hydroxides are slightly soluble. Again, that means that in most cases, they're going to be considered insoluble. If you have carbonate, phosphate, and sulfides, they're going to be insoluble, except if they are with group 1 or unless they are with ammonium, which again is our kind of rule on the first page. So if you kind of remember that rule on the first page, a couple of rules there, the group 1 and ammonium, it will really help you out with the kind of insoluble guys, because if it's not one of those guys, then it probably is going to be insoluble if it's one of those carbonates, phosphates, or sulfide. So for example, if we were to look at, we'll do silver nitrate plus some sodium chloride. This is a double displacement reaction that makes silver chloride plus some sodium nitrate. So let's just say we got our double displacement. By the way, this is a positive negative guy, right? Positive negative. They basically switch partners, right? And that's how we get to the other side, basically. So here's what we want to look at, right? We take a look and we want to decide solubility. Should we put, again, AQ? And if we do, that is something that's soluble. Or should we put S, which is solid, for something that is insoluble? So when I look at silver nitrate, although I may not be able to find silver by itself, I can find nitrate on my list. And if I come back here to the previous slide, I see nitrate is soluble in everything. There are no exceptions, which means that automatically tells me this guy is going to be a solution and going to get the aqueous symbol. I come to my sodium chloride. I look at my sodium, and again, sodium is group 1 on the periodic table, and that is something that's always going to be soluble. There's no exceptions, so I automatically know this guy is going to be soluble. Now, let's just say you wanted to look at the chloride, and you definitely could look at the chloride. So if I look at the chloride, based on the solubility rules, chlorides are soluble except when they're hooked up with silver, mercury, or lead. And in this particular case, it is not silver, mercury, or lead here, right? It's sodium. So that also tells me the same thing, that it is soluble in this case. So you can actually look at either one if you can find them, both of them on the solubility rules. And if we come over here, we're going to look at chloride like we just talked about. That is going to be soluble in everything except for silver, mercury, and lead. In this case, though, my chloride is hooked up to silver, which means instead of being soluble, this is actually now going to be the opposite and become insoluble. And this would be our solid that is formed here, a white solid that would actually form in this case. Because in this case, chloride and silver, when they come together, will actually drop out of solution as a solid because of these sort of attractions. I come over here, this is sodium, and frankly, that's as far as I need to look. I know this is going to be soluble because it's group 1. I also could look at nitrate, which also has no exceptions, going to be soluble in everything, and it will tell me the same thing. So this is how you could use these solubility rules to determine whether you have something that's going to be a solution, no solid, or you're going to have something that's going to make a solid. So once again, if we were to toss these guys into our beaker here, we would get basically some silver ions, some nitrate ions, we would get some sodium ions and chloride ions. And what's going to happen in this case is these two guys are going to go find each other, and based on those solubility rules, they are going to precipitate out of solution. That's going to leave my sodium ion and my nitrate ion floating around, which if we look back, looking for somewhere to write that, I'll do it right here. If we look back at our ionic equation, we could actually write that. So we take sodium chloride, silver chloride, and our sodium nitrate. So this again is our molecular equation, right? We write our total ionic equation. This would be silver with a +1 charge. This would be nitrate, the -1 charge. This would be sodium with a +1 charge. This would be chloride with a +1 charge. Once again, we hit a solid, which means we want to keep it together. we would not break it apart. And then this guy here, sodium would break apart, and nitrate would break apart as well. This would be our total ionic equation. And as we can see here, that is our nitrate, that is our sodium on both sides, which look exactly the same. These are our spectator ions. And if we look back at my picture I drew a second ago, that is what we see. There's my sodium ion just floating around watching, and there's my nitrate ion, right? Just floating around watching. It is not involved in making that solid that we see here. And that is why they're referred to as a spectator ion in this case. And obviously we could cross these guys out, and that leaves us our net ionic equation, which in this case, as we talked about, it is basically the silver ion from the silver nitrate is going to find the chloride ion from the sodium chloride, and those two are going to come together based on solubility rules and make that solid precipitate here that's happening in this reaction. And again, that is our net ionic equation. As you can see, when you write your total ionic equation and your net ionic equation for things that are ions, like anything that's an ion by itself, you do need to have the charges, yeah? So pluses and minuses need to be there, hence the name total ionic equation, right? Net ionic equation. There should be ions present, and there should be charges on those ions. We still don't have charges on things that come together that make the solid or anything like that. Any question on that there? All right. So here's also a solubility table. It's pretty much more of a table than the words that we were just looking at. But again, if we look at it, it works the same way. These are all guys over here that if you're on the left-hand side, these are things that are soluble that gets the aqueous. But if you're over here, these are guys that are going to be solid in this case. Down here, these are guys that are typically solid on the left-hand side. But if you have somebody on the right-hand side here, they will be aqueous, yeah? So that is, again, kind of more of a table version of the words, so that might be easier to kind of remember. Obviously here they want you to remember everything, so you do need to know the solubility rules, so make sure that you do know these guys. Question on that there. Okay. So let's talk about acid and base reactions, and acid and base reactions also fall under the double displacement category. And acid-base reactions account for, as we will see, basically the formation of water. And as we were talking about, 3 reasons why a reaction takes place: formation of a solid, formation of water, is really double displacement sort of territory where this occurs. So acids have a sour taste. They react with litmus paper and turn it red. So usually blue litmus paper to red. They react with certain metals to produce hydrogen gas. Dare I say we saw that on Monday, where I took the magnesium and I took the hydrochloric acid, and I was holding the test tube going, wow, that's pretty hot. All right. And we lit the splint there. And the splint started to bark, and it barked because we produced hydrogen gas, yeah? And that is what the bubbles were when the magnesium were reacting. Aqueous solutions conduct electricity, so we have strong acids, which are strong electrolytes. We have weak acids, which are weak electrolytes, and again, they both will conduct electricity. The definition really of an acid is the ability in a solution to basically produce H+. So that is sort of your basic definition of an acid. It is something that when it goes for a swim, will have the basically ability to produce free H+ ions or hydrogen ions in solution. Bases, on the other hand, have a bitter taste. Don't taste any of them. They do feel slippery. A lot of soaps, drain cleaners, these are all bases. They change litmus paper to blue. So if you use litmus paper and it turns blue or stays blue, it is basic. There are strong bases and weak bases, which again are electrolytes as well. Again, strong bases going to 100% break apart, and weak bases will mainly stay together. So when we have an acid, again, our list of strong acids that we talked about there, Those six are hydrochloric, nitric acid, sulfuric acid, again, hydrobromic, hydroiodic, and perchloric acid. Once again, that list of six are really good, important list to know. Again, as we talked about, when they go for a swim, the reason why they are strong acids is when you pop something like hydrochloric acid into the beaker, it is just gonna break apart into ions, basically. And it's going to produce a lot of free H plus ions in solution really, really quickly, which is why it's considered a strong acid, because basically it breaks apart, boom, lots of H plus in there, makes it really acidic in that case, and will actually lower the pH a lot because of that, because you basically just added a bunch of free H plus. That's really what affects something like the pH of a solution, making it more acidic or less acidic, is how much of that free H plus, not attached to anything, just freely floating around in that solution. And a strong acid, just by the process of it breaking apart completely, will produce a lot of H plus really, really quickly. Bases, on the other hand, are things that typically will produce hydroxide in solution. And that is essentially the purpose of a base, is to produce free hydroxide. Sodium hydroxide, which is a strong base, and it went for a swim, it would break apart into sodium ions, but more importantly, it would produce a lot of OH minus in that solution, freely floating around. And the production of free OH minus in a solution is something that makes it a strong base, because OH minus and H plus, as you'll learn eventually, they are related to each other. So as one goes up, the other goes down. So when you add a strong base to your solution, you produce a lot of hydroxide, which means the OH minus concentration goes up, the H plus drops a lot. And what you see is actually the pH will go up a lot, because it now will become more basic, because you have a lot more hydroxide in the solution. So this is why something like sodium hydroxide, again, is a strong base, because all it has to do to basically make that happen is go for a swim. It's going to break apart, and boom, you're going to have a lot of hydroxide in that solution really, really quickly. Now, what happens when you react a strong acid with a strong base? Well, whenever you take basically a strong acid and a strong base together, and in most cases, when you take an acid and base together, you basically produce two things. You produce a salt and you produce water. So pretty much that's always what is produced. And this, again, is the second reason why a reaction takes place. You're making water, basically, is the idea here. This is also why it's sometimes referred to, this reaction of a strong acid and a strong base, as an acid-base neutralization reaction, because essentially you're going to be making water in this case. So what happens? Well, if you took something like hydrochloric acid, which is a strong acid, and you react it with sodium hydroxide, which is a strong base, this is an acid-base neutralization reaction. It is also, again, still a double displacement reaction, positive, negative. We are going to get, again, a switching of our partners here. And what we're going to form on the other side is the sodium chloride, which we know is going to be aqueous based on our solubility rules, and we will form water here. And this is our molecular equation, right? We could also write a total ionic equation for this. Because HCl is a strong acid, it will 100% break apart into H plus and Cl minus in solution. The sodium hydroxide, also a strong base and a strong electrolyte, will break apart into sodium ion and a hydroxide ion. So if we draw our little beaker view of what's happening here, we have our H plus and our Cl minus from our HCl floating around. And we have our sodium ion and our hydroxide ion floating around from our base. Now, what's going to happen on this side is this is also going to break apart, because it is a strong electrolyte. And we'll get our chloride here. And now water, which is a pure liquid, will actually stay together. So we do not break apart, again, anything that's a solid or a liquid. And this is our total ionic equation. By the way, a salt is a fancy word for an ionic compound. So the sodium chloride here is our salt, and obviously This is our water in this particular case. Now, if we look at our total ionic equation, we could find our spectator ions here. And our spectator ions is our sodium and our chloride in this case. These are our spectator ions. And we could cross those out. And we are left with ultimately what is happening here. It is the H plus from the acid always. Going to hook up with the hydroxide from the base. And H plus and OH minus makes our favorite thing, which is water here. And this is our net ionic equation. So when we dump these guys together, it is the H plus from the acid that's going to go find that OH minus from the base. I'll scratch it together, but it's basically going to make water in this case when those guys come together. The result of that is, as you can see in my picture, just like we've talked about, the two ions kind of left out of the action, chloride and sodium just hanging out watching, which are spectator ions in this case. And again, they're still there, they're floating around, but they're really not making anything. They're just kind of, truthfully, they're there just to balance out the charge of everything, but they're just kind of floating around in a solution, not making our product. You could take any combination you like of a strong acid reacting with a strong base, and you could go through the total ionic equation, and every time you should always end up with your net ionic equation as this. This is ultimately what is happening here. And really, again, the second reason why a reaction is taking place, we are ultimately forming water, which, as I mentioned before, is why this is sometimes referred to as an acid-base neutralization reaction, because ultimately you're making water basically in this case. Yeah. Any questions on that? Yeah.
This type of stuff,
Yeah.
we don't have to write the net equation, or do we write it all?
It depends on it. I probably will ask you to write all three, to be honest with you. And sometimes you'll have questions that will just ask you to write just the net ionic equation. So there is a sort of a back way you could kind of get there if you kind of know what's made and kind of work backwards. So for example, if I know in this one water was made, I know if I break apart water, it's basically those two ions, and you can kind of get there. Just like, for example, when we had the solid of this guy, if I knew, for example, actually that wasn't the solid, we had the ion. We'll do that one. It's the same thing. If I knew that was a solid, technically I could kind of work my way backwards. It goes and this, right? And I could just write the net ionic equation, kind of working backwards. Idea is kind of go forward so you don't mess up. But sometimes you'll be asked for just the net ionic equation. Sometimes you'll be asked for all three of them. And obviously sometimes you'll be asked for just the molecular equation. So any combination there, yeah. You should in most cases. So you want to use those solubility rules again to help you decide, what it's going to be. In most cases, on most of these acid base or precipitation reactions, it's going to be either aqueous or solid, basically. You usually don't have too much gas or, those type of things in there. But you may have like a weak electrolyte, which again, you would not necessarily break apart. So just to show you that, actually, I'll do it on this one. Let's say we did not hydrochloric acid, but we did hydrofluoric acid, which is a weak acid. Again, by the way, I know it's a weak acid because I know that list of 6 acids, and it's not one of the 6. Yeah, so it's not one of the 6. I know this is going to be actually a weak acid. And we can react it with sodium hydroxide in this case, which is a strong base. By the way, it is still a double displacement reaction, so we're still really just going to switch partners here. So these guys are going to come together, and these guys are going to come together. So on the other side of the arrow here, we do just want to think about the basic units there. So that's going to give us water. And then the sodium, which is +1, and the fluoride, which is -1, will come together to make NaF. And I know that has sodium in it, so I know it's going to be aqueous, right? So based off those solubility rules. So that would be our molecular equation in this particular case. So if I were to do my total ionic equation, when I look at the HF and I know that's a weak acid, that also means a weak electrolyte, which means it's going to actually stay together, right? It's not going to really break apart. It is going to break apart just a little bit, but mainly stay together in solution. So we would not, for example, break that guy apart in this equation. We would keep it together because it's a weak electrolyte. So unlike normally we would break apart into H plus, F minus, in this case we wouldn't because it is a weak electrolyte. The sodium hydroxide is still a strong electrolyte, so we would break that guy apart. Our water is a pure liquid, so we would keep it together. And our sodium fluoride would also break apart here into sodium and fluoride ions. And this would actually be our total ionic equation in this case because of that weak electrolyte actually being there. Now that also affects, for example, our spectator ion. In this case, what is our spectator ion? It is just the sodium in this case, right? So again, if we were to draw a picture of this and we take the HF and we take our sodium hydroxide, basically we're going to have mainly that in solution, and then we'll have this and we'll have this, but this guy will also break apart just a little bit into those guys, basically. So that is where we still have the ability here to form our water, is from the little bit of H plus that basically comes off. And we do have HF still there, and we still have sodium basically flying around. We are ignoring this. It's going to be a kind of a small amount in this case. And we are left with HF plus hydroxide making water and our F minus, right? I guess I didn't need to erase that guy. It's right there. And you can see at the end, we have all those things in there. Again, these guys are going to basically make a little water in this case. And this would be our net ionic equation. So having that sort of weak electrolyte present will actually cut down on the number of spectator ions you have. And in this case, it's actually just the sodium is our spectator ion basically floating around. Yeah. Yeah, you probably won't come across too many of those at all because, yeah, you want to, you really for these two reactions, it's either going to be a strong electrolyte, which for our class, probably most of it is going to probably be a strong electrolyte, but our weak electrolyte will pop in there occasionally. As you go into more chemistry down the road there, 1A and 1B, you'll definitely see a lot more probably weak electrolytes pop in. But most of ours will probably be strong, but they might still throw some weak electrolytes in there. And that's basically how you handle it. You kind of keep them together. It works exactly the same. You would keep it together. So if you did something like hydrochloric acid, which is a strong acid, plus ammonia, that's going to make some ammonium chloride basically when this comes together. And in this case, we would break apart this guy. We would break apart this guy into those two. This is our weak base, which means we would actually keep it together. This is basically a salt that will break apart into these guys. And you can see now it is the chloride that is our spectator ion in this particular case. That leaves us our H plus and our NH3 gives us NH4 plus, and this would be our net ionic equation in this case. And that's ultimately what's happening is it's actually a acid-base reaction. It's basically a proton being transferred over to the NH3 is going to pick it up and accept it. So it's known as a Bronsted-Lowry acid-base sort of reaction, and that's ultimately what's happening is that proton actually being transferred over to the NH3 and it'll accept it. Question on that there. All right. All right. So again, a reminder that you always make a salt in water, and a salt in most cases based on solubility rules, I would say probably 99, maybe even more times out of 100, the salt that you'll come across with an acid and base will be soluble, aqueous. It is possible for it to be insoluble, but most of the time it is definitely going to probably stay together and be soluble. All right, it's probably a good stopping place there.